So here's the idea for area between two curves. If you have two curves, and here we have two parabolas, you could draw them with a graphing calculator or just get an idea in your head. And in fact, for this one, can you see that one of the parabolas is going to open up and one of the parabolas is going to open down? Because one of them has a positive x squared and one of them has a negative x squared. So as a possibility, it could have been that the blue one was like this and the red one was like this, and they never intersect and they never have an area between them. But since it says find the area between the curves, it's most likely that you'll have something like this. And you'll be wanting to find this area in between. Now, up till now, we have been doing area under a curve. And that area under a curve always went to the x-axis. So if I'm just going to erase this yellow part for now, and I'm going to say, well, if I want to find the area between the curves, this point and this point, where they intersect are going to be important. And if I first do the red one, and I said, let's find the area under that curve between those two black lines, does it make sense that you would find all of this right down to the x-axis? That's what we were doing the other day. And then if you wanted to find the area under the blue one, and the same thing, you would find all of this. The idea now, if I want to find the area between them, does it make sense that if I just erase the area or subtract the area underneath, then I'm left with the area in between them. So that's the idea. We have, basically what I did was here on the right-hand side. I took the area of the one on the top, the whole thing, right to the x-axis, and then I subtracted the area of the other one right down to the x-axis. Now, some of our properties of integrals is we learned before that if you're subtracting two integrals, you could have had those integrals inside or those functions inside to begin with, and that's going to make our life easier because if we can simplify a little bit inside, the integration is just going to take a lot less time. Okay? The other nice thing about the area between two curves, you know how last time, let's say, I'm going to move this out of here for now. I'm going to make, let's say your two parabolas were like this, and your axes ended up being like this. And you're like, oh, we had a special case where when one was above and one was below, we had to figure out where the x-intercept was and then go from there to figure out the curves. Well, the nice thing about the area between the curves is when you subtract the two, it actually doesn't matter if it's above or below the axis. So in this case, whether these black axes were here, or whether they were here, or whether they were over here, it's going to be the same idea. You're going to be able to figure out the area between them no matter where your axes are. The only thing that we're going to have to figure out differently is maybe sometime you'll get a cubic equation like this and another function that goes like this. Now you have to figure out those two areas separately because in one case the blue function is above, in the other case the green function is above. So there's some background idea behind the area between the two curves. Now that we have that idea, we can say, well, I know that this red graph is going to be the one on the top. And so we've sketched everything and we can put it in. Find the intersection points. So we'd set our two equations equal to each other. You're going to find out that in this case, it's at -2 and 2. That's going to help us set up our integrals for subtracting. And again, we're going to put the one that's going down first because that would be the function on top. If you screw up and put the wrong one first, it doesn't mean you have to redo all of your work. In the end, your area will be negative as a result because you're having the smaller area subtract the bigger area. So if that's the case, instead of erasing everything on the way back and redoing it, you could just put absolute values bars around your original function and it'll work out to be the same thing. So again, the nice thing about putting both functions inside the same integral is we can now simplify. Once we've simplified, doing the integration is just easier. You're finding it from -2 to 2. Plug your values in. Again, I like to, before I simplify inside the brackets, see if there's sort of some like terms. In this case, there's going to be. And we get a final answer as 64/3 units squared. So first of all, looking at those two functions, can you see that y equals x squared? That's a parabola. Does it open up or does it open down? It opens up. So we're going to have a parabola like this. Next, we've got y equals x plus 1. That's a line. I'll draw them separately for now. It has a positive slope, so it's going to be going up from left to right. If you're going to find the area between those two curves, which function would have to be on the top? It would have to be the line, right? Otherwise, they don't intersect. And then the area between them would be infinite because it would keep on going forever and ever and ever. So we're going to start with the assumption that if they do have an area between them and they do intersect, then the line would be on the top. Here's a picture of our graph in the graphing calculator. Sure enough. So now to find the area between those two curves, we're going to need to find our intersection points, set up our integral, integrate, and go from there. So I'll give you guys a head start. And again, the nice thing that we talked about before, the fact that some of this area is below the x-axis no longer matters. And we'll talk about that a little bit. Well, let's talk about it now. If I did the areas separately, okay? If I did the area from the red one, that would give me this area. If I did the area from the other one, the other curve would give me this area positive and this area as negative. So when we subtract the green, subtract the blue, well, when I take the green and I subtract this positive area over here, that just goes away. And when I subtract this negative area, the negative area becomes positive and just adds it on. So it ends up finding the area between those two nicely. So if you found your intersection points so far, should have got 4 and -1. And then you can set up your integral. We'll check your integration, and then I'm not going to worry about whether or not you've plugged everything in. When you've integrated it, this is what you should have got, x cubed over 3, well, minus x cubed over 3 plus 3x squared over 2 plus 4x. And we're going to trust each other that you could plug those values in, use a calculator, and solve them to get that answer. One of the things you should be thinking about is if this was a calculator question, which usually these ones aren't because they'll give you numbers that are that are nice enough and they want to see that you know what's happening. But if it was a calculator question, how could you use your calculator to help you solve this? Okay? Again, this last example, we have a parabola and we have a line. The parabola is going up, so again, when we think about it, we've got this situation. So we have to find our intersection points, set up our integral. So again, I'll give you some time to practice finding those intersection points and setting up your integral and integrating. Then we'll put up the answers to have a look. If you get done early, see what you can do with your calculator to make it go faster. Did you find your intersection points to be 2 and -2? Excellent. No, you don't have to find the actual points, but they're just there to help us see it on the graph. Then finding the area, you subtract the 2, you got -x squared plus 4. And then solving it, 32 over 3 is your area squared.